Okay. Let's talk Unit 2 in dynamics. This will be a short content review, but we spent a lot of time on the few concepts that were in this unit. Okay, first thing we went over in Unit 2. Newton's first law. An object at rest will remain at rest. An object in motion will remain in motion at a constant velocity unless acted upon by an external, unbalanced, or net force. Okay, so in other words, Newton's first law deals with all situations in which the net force equals 0. Okay, what word do we use to sum up Newton's first law? Inertia. Okay, Newton's first law is inertia. Okay, so inertia. Basically, what happens when there are no net or unbalanced forces? Okay, there's no problem solving to do with Newton's first law. Okay, it's just what we have to understand. Okay, we did also learn how to draw free body diagrams on that first day. Okay, basically we draw a box, we put the mass inside the box, and we draw the forces as though they originate from the middle or center of mass. Okay. And then we went on to what would comprise half of the unit. Newton's second law. Okay. Newton's second law deals with all the situations where there is a net force. When there is a net force, what will the object do?
Accelerate.
It will accelerate. Okay, there will be some change in velocity, whether it's increasing or decreasing. Okay, it's going to be a change in velocity. So F net equals mass times acceleration. What was the other way?
The sum of both.
Right. The vector sum of all forces. And that was the part of Newton's second law that could produce the difficulty in analysis. Okay, we had to be able to look at a situation, identify what are the forces that are acting. Okay, how do they produce the final acceleration of this object? Sometimes that meant having to draw a vector diagram, putting those forces tail to head. Okay, other times it meant, drawing a picture of something sitting on an inclined plane, or with a pulley in the middle, or just a sign that was hanging there. Okay, we dealt with all kinds of different situations, okay, where the net force was not 0, okay, or in some cases was 0. Okay, some of our Newton's second law questions were really Newton's first law questions. We just had to find one of the forces that contribute to the net force being 0. Okay, so that would have been like the signs that were hanging, any of those static condition examples, okay, where the force is all balanced out. Okay, does that make sense? So there was a couple of places where there were key words in a question that we would have to look for and be aware of. Like a box is sliding down a plane at a constant velocity of 2.5 meters per second. What's the net force in that question? 0. Because it was traveling at a constant velocity. Didn't matter what that velocity is, okay? It just mattered that it was constant. That meant A is 0. That means F net is 0. That means the vector sum of all forces is 0. Okay? And then usually in a question like that, we'd have been asked to identify one of the forces acting on the box. Okay? And then in other situations, we might be given the acceleration of the object and asked to find one of the forces contributing to the acceleration. Or we're given all the forces and we're asked to calculate the acceleration. Okay? There was any number of ways those Newton's second law problems could go, but we did a lot of them. All right? So expect at least a couple of those. Okay? One of the questions that's Newton's second law is quite straightforward. The other one is quite a bit more involved. Okay? So be ready for both kinds. Okay? By quite straightforward, I mean like there's very few forces involved. Okay? One that's more involved, there's many forces involved. Okay? It doesn't mean that it's any like different. Newton's second law is Newton's second law. Okay? Just there's more to deal with in an involved question than in something like, you know, a box slides to a stop on a level floor. Okay? Well, what's bringing it to a stop if it's on a level floor? Friction. Okay, well then my net force is friction, right? Like that's a simple situation. There's only one force acting. It's the net force. That's a simple one. Okay, an involved one could be you're pulling a box up a ramp and there's friction and blah blah blah. Well, now there's like 3 forces involved, 5 forces involved. Okay, do we have to identify them all? That would be more involved. Okay, doesn't mean that it's any like more difficult. It just there's more stuff to be aware of. All right. After like 2.5 weeks of Newton's second law, we did a lab with the pulleys and the carts, and we looked at what the acceleration of the carts were based on increasing applied force over the pulley. Okay. Then we moved on to work energy theorem. Right? And that was kind of a review from Science 10. Okay. But we had situations where both kinetic and potential energy were changing at the same time. Okay, so if we accelerated a car up a hill, okay, we would be changing both its kinetic and potential energies. So, work energy theorem goes like this. Work is a change in mechanical energy. Okay. Which would then look like this. Work is the final mechanical energy minus the initial mechanical energy. Okay. In a law of conservation of energy question, those two numbers are equal. There's no change because energy is conserved. Okay? In a work energy theorem question, energy is either being put in or being used to do something and being lost. Okay? That's why there's a change. Okay? So we could expand that out even further. There's another formula for work. What is it? Force times distance. Okay? And how do we calculate mechanical energy? Mechanical energy. Yeah, potential plus kinetic. Mechanical energy is your sum, the sum total of your kinetic and potential energies. So we would have EP final plus EK final minus in a lot of the questions we did, the final energies were like 0 or the initial energies were 0. It kind of made it a little bit less algebraically involved. Okay? But this is what it comes down to. Okay? Sometimes it expanded all the way out to this. Okay, and then we would be asked to calculate one of the variables. Okay, so maybe the question was, if we're accelerating a car up a hill, okay, we would have been told how long the hill is. We would have been told that it started at the bottom and went to a height of 20 meters and started at 4 meters per second and accelerated to 9 meters per second. Okay, what was the force used? Okay, well then I was told the length of that ramp, that's the distance over which the work was being done. I was told I started at the bottom, so my HI was 0. Okay, I was told I started at 4 meters per second. That would be my initial velocity or initial speed, sorry. Okay, and then I was told at the end I was 9 meters per second, and I think I said 8 meters higher or something like that. Okay, so I was given basically everything on this side of the equation and the length of the hill. Solving for f would have just meant dividing the whole side by d.
Yes.
Okay, sometimes they were that easy. Okay, other times it could have been I got all this stuff except for hi. Well, that's a little bit more algebraically involved, but in the end, it is just algebra. As long as I have all those numbers, I just have to move things around to isolate. Okay, ringing a bell? Okay, we didn't spend too much time on that because we had done some of that in Science 10. Okay, and then we ended off with conservation of energy. So that was number 3, right? Yeah. Okay, and that was totally review of Science 10. We did nothing new with the law of conservation of mechanical energy. Okay, so that could be like a roller coaster question, or a kid going down a hill on a sled, or a bomb being dropped out of a plane, you know, or like any number of situations where only gravity is causing the change in energy. Okay, there's no friction or anything like that. So the energy at the beginning and the energy at the end are the same. Okay, so you'd either be asked to solve for a height or a speed. Okay, because when it comes down to it, this is what we have. Okay, that would also be true for a pendulum. Okay, because law of conservation of energy was in 2 units. Okay, it was in this unit and it was in unit 4 as well. Okay, I'm not going to test it in both, but it's definitely on the final. Okay, good news is the principle is the same for both. Okay, all that changes is whether you have gravitational potential energy or elastic potential energy. Okay. So in a question like this, you'd be asked for either a height or a speed and be given the others. All right, that's what's on the final from Unit 2.
So in the law of conservation of energy, you can cancel out the masses, but in a work energy theorem, you can't because they're subtracted.
Not because they're subtracted, but because m's not in every term. It's not in force or distance. Right? There's the other side of the equation there. So yeah, I can cancel it as long as I'm not looking for an energy.
Okay.
Like if I set up one of those conservation of energy questions and then said, what's the final potential energy? You can't cancel m because mass is part of joules, right? The reason you can cancel m is yes, it's in every term, but also the heights and speeds are independent of mass. All things accelerate at 9.81 regardless of the mass. That's why you can do it. Does that make sense?
Yeah.
All right, other questions from you guys? Anything you'd like me to go over or demonstrate?
Is Newton's third law in there as well?
Newton's, oh yeah, I forgot Newton's third law. Okay, we did go over Newton's third law. There's no problem solving to do with Newton's third law in the final. That's why I forgot it. Okay, but there is a multiple choice question. I think just one. Okay. So there's no like 2 boxes, you know, you push on box A and box B, box A pushes on box B, and yeah, that there's none. There's one of those on your unit exam, there isn't one on the final. So, Newton's third law, every action has an equal and opposite reaction. Okay, let's just write that down. We're out of order here, but. Okay, and Newton's third law is, of course, where we learned the origin of normal force. Okay, normal force is that reactive force that results from one thing pushing on something else, right? Forces always act in pairs, action, reaction pairs. Okay, what else? Can we throw a few questions on the board?
Can we do a work energy theorem question?
Work energy theorem question? Nope, that's a Newton's second law question. That one. Yeah, I'll just make one up. Okay, so this box, this 20 kilogram box is starting at the bottom of the ramp. At 1.5 meters per second. The ramp is 12 meters long. Sorry, I gotta do a little bit of math in my head. That might be a lot, but it'll work. It's better to be too big. Okay. All right, box is being pushed up a frictionless ramp. Okay, the ramp is 12 meters long. When it gets to the top of the ramp, it's 4 meters higher and has accelerated from 1.5 meters per second to some speed that you must now calculate. Okay, so obviously work is being done because the energy, the mechanical energy of this box is being increased, right? It's not only going up the hill where it would have more potential energy, it's also being accelerated and going faster, right? So I know then that it is a work energy theorem question because the energy at the bottom and the energy at the top are not equal. Okay, everyone all right with that? I mean, if this thing had started at the bottom at 20 meters per second, and by the time it got to the top was going 0, it could be a law of conservation of energy question then. Okay, but in this case, it's actually being pushed up the ramp. Okay, so in that case, then I'm going to have force times distance equals the change in mechanical energy. So that will be m times g times h final plus 1/2 mv final squared. Okay, minus m times g times h initial plus 1/2 mv initial squared. Now, are any of these 0? Which one?
Energy potential initial.
Yeah, the potential energy initial. It starts at the bottom of the ramp. Hi is 0. So I can get rid of that right now. That simplifies things a little bit. Okay? And I'm going to get rid of that plus sign as well. Okay, so now I am looking for this. Okay, I'm looking for VF. So what I would do first is I would add the initial mechanical energy over to the other side. Right? So I'm going to have the change in energy plus the initial mechanical energy equals the final mechanical energy. That makes sense. I mean, that's work energy theorem, right? If I take how much I change it by and add it to what I started with, I should get what I have at the end. Okay. I'm looking for VF, so I'm going to subtract MGHF over to the other side. Okay? Because this is my potential plus my kinetic. I want to subtract my potential over, so I'm looking for my kinetic. So I'm going to have force times distance plus 1/2 mvi squared minus mghf equals 1/2 mvf squared. Okay, so basically I'm saying, here's my mechanical energy minus my potential energy, that will equal my kinetic. I want to get VF by itself, so I divide both sides by half of m. Okay, it does not cancel, right, because I'm adding and subtracting on the top. Okay, so half of m comes over, even though I've got a half of m on top, it doesn't cancel here. Okay, and then I square root. Okay, so what I'm going to have in total here is 800 times 12 plus 1/2 times 200 times 1.5 squared minus 200 times 9.81 times 4 divided by 100, half of 200. Okay, and then I'll square root the whole thing. Everybody with me there? Or sorry,
Yeah, I was.
10,
Yeah.
not 200. 10 is 20 kilograms. Okay. That's what I'm looking for, that thing. Okay, so we're going to have 800 times 12. Right, plus 0.5 times 200 times 1.5 squared minus 200 times 9.81 times 4 and divided by 10. It's going pretty fast. But I used a lot of force. I made sure my force number was big enough that this question worked. In the past, I've made the force too small and it doesn't go up the ramp, and it just works out poorly. Okay. All right, so at the top of the ramp, it's going to be moving at 14 meters per second. Okay, because we do a lot of work. 800 newtons is a lot of force. Okay, over 12 meters, that's doing a lot of work.
This is just a question. So, with your acceleration due to gravity, like 9.81, how come that isn't negative? Like
Because
it's not-
work and energy are scalar.
Oh, okay.
Yeah.
So it just doesn't matter.
Yeah.
Okay.
Was the mass 200 or 20?
Did I go 200 again? I
think
did.
so.
I see it 200 times 9.81. I had that in my head, even though I wrote it as 20. So do I get a much bigger number then?
Yeah, you get. Like, did you get 29?
I did, yeah.
Yeah. Okay.
Okay, let's try that again. 800 times 12 plus 0.5 times 20. I wrote 200 in there. That's why I did, because I wrote 200 in there. Okay. Times 20 times 1.5 squared. Okay, minus 20 times 9.81 times 4 divided by 10. Wow, even faster. Okay, 30 meters per second. Okay, so yeah, it's being shot up the ramp. Okay, what else?
Are you doing like the conservation of energy?
Mm-hmm. That's too big. 8 per second. Okay, so we got a roller coaster at the top of the first hill, moving at 8 meters per second. A little while later, it's 6 meters off the ground, moving at 34 meters per second. I want the height of the first hill. Okay, so we start out, we know this is a conservation of energy problem because there are no forces other than gravity causing the change in energy. Actually, there's no change in energy causing the change from potential to kinetic, basically from the top to the bottom. All right, so we have initial potential plus initial kinetic equals final potential plus final kinetic. Okay, what we're looking for is part of this term, so I'm going to subtract the initial kinetic over and have this. mghi equals mghf plus 1/2 mvf squared minus 1/2 mvi squared. Okay, then I'm going to cancel the m's because they're irrelevant for this question, and then I'm going to divide both sides by g. That will give me my initial height. So when I plug in my numbers, okay, I'm going to have 9.81 times 6 plus 0.5 times 34 squared minus 9.81 times 8. Sorry, not, sorry, 0.5 times 8 squared, sorry. And then I'm going to divide that by 9.81. And there was the initial height of the roller coaster, 62 meters. Yeah, actually, there's only one significant digit the way I wrote that, but I would never do that to you on a test. Okay. All right, questions on that?
Is there going to be any bank credit questions?
Possibly. Yeah, I mean, that was one of the two types of curves we went over. So, could be a question we can go over tomorrow. Okay. So remember, guys, the plan for tomorrow is you come to me with things you want to review. Okay? Because we've reviewed everything now. Okay? So you come to me with stuff you want me to go over. Okay? And I will make up questions, put them on the board. If we run out, then I've got some in the bank here that we can go over. Okay? And see. But you'll get more out of tomorrow if you come with questions that are pertinent to you, rather than me trying to guess. Okay?